Okay. Okay. All right. Right. We continue from where we left off last time. We talked about norms, right? We talked about the p norms of a vector. Okay, and we said it's represented like this, right? What is the definition of the p norm? Have the sheet with you if you don't remember, but try your best to recall from memory. Yes. So 1 to n xi, but absolute value. Yeah, good. Okay, all right. That's the definition of the p norm. Okay, we know what the 2 norm looks like, right? Yeah, you simply right. Uh, the 2 norm. So it's like so. Let me write the square of the 2 norm is simply say square. I don't have to take the absolute value because square is always positive. But if it's 3, then you have to take the absolute value because cube of a negative number can be negative, right? That's why in general you have the absolute sign. Sorry. No, I've squared it here, right? So this is okay. But this is also equal to this. No? What is the definition of the inner product? Or what is this defined as? Yeah, look at the sheet. If you don't remember, look at it. It's xi, yi, right? If both of them were x, then this will simply be summation xi square. So the 2 norm, square of the 2 norm is also this. It's simply the inner product of the vector with itself will simply be square of the 2 norm. All right. So with that, we will now move on to another important topic on orthogonality. Right? So essentially the idea of two vectors being perpendicular to each other. That simply stands for perpendicular. Okay. Okay. So we'll see what is the condition for orthogonality and how it's connected to the idea of the inner product. Okay. Now, if you let's say I have a vector like this, I have another vector like this, x, y. Okay. Let's say they're perpendicular to each other. Okay. And the length of this vector is the 2 norm. Let's say I'm using the 2 norm. This is square. Right? I can think of a vector like this. Okay, starting from the tip of y going to the tip of x, and this vector will simply be minus y. You can verify how that is. I won't explain why that is. Right? What will be the length of this? Let's say we are working in R2. If you have two lines that are orthogonal to each other, what will be the length of this line that joins these two tips? Sorry? Root of square of this plus square of this. Is that what you say? How did you say that? Oh, yes. What is the rule? What is the law or theorem? Pythagoras' theorem, right? Right. The square of the length of your hypotenuse is the sum of the squares of the lengths of the individual sides. So this is simply equal to right. But we know what this is, right? We know x minus y square is simply transpose x minus y. Okay. For now, assume that this transpose operation, this p operation can be taken inside. So this will simply be y transpose y. And if you multiply this out, what will you get? So you product this. So it will be x transpose x and then x transpose with minus y. This will be y. And then these two. and then these two, but the plus. Okay. We know what this is, right? We know what these two are. What are these two? Well, it's simply the square of the two norm. If you remember, one of the properties of the inner product in Rn is that it's commutative. X transpose y equals y transpose x. That means I can combine these two and simply write it as 2 times x transpose y. Okay. But because x and y are perpendicular to each other, I know that this must be equal to this. If this is equal to this, then this has got to be 0. Right? That means x transpose y equals 0. And that's the condition for orthogonality. You say two vectors are perpendicular to each other whenever their inner product comes out to be exactly 0. Okay. Okay. And this applies for Rn in general. Okay. Even though we've used an example from, we started off with a visual example in R2. The algebra works in Rn. Okay. Because there is nothing here. There is nothing here where I've assumed that the vectors are only from R2. Okay, and so this is the condition. Right? And there's something that's important that you need to remember, that if the standard inner product between two vectors is 0, that means they are perpendicular to each other. See, that is the case, right? Then you could ask, okay, we only looked at what the standard inner product is defined as algebraically. Now this tells us that maybe the inner product tells you something about the angle between two vectors, right? Because when they're perpendicular, it comes out to be 0, and that is in fact true. The standard inner product, I'll write it as IP, provides measure of angle between two vectors. Angle between x and y. If you have two vectors like this and y, and let's say the angle is theta. This is in any Rn, not just R2. Okay. The standard inner product, we know that you can compute it like this. Yi, this is actually equal to the length of x measured by the two norm, the length of y measured by the two norm, and multiplied by cos theta. Okay, cos of the angle between them, and this in fact agrees with this, right? Because when theta is 90, cos is 0, right? And this is equal to 0. Okay, but this also means if I take my x transpose y and I ask what is it, so here these two are positive numbers, norms. What values can cos take? What possible values can you get if you compute cos of something? It's between, will always be between plus and minus 1, cannot be greater. Okay, this is positive, but the inner product itself can be negative, because this can be a negative number, right? But if I take the absolute value, and I take the absolute value of this, if you have two real numbers a, b, the absolute value of this is simply the product of their individual absolute values. That means this is equal to the absolute value of this multiplied by the absolute value of this multiplied by the absolute value of this. These are anyway positive numbers, right? So this will simply be x2 y2 multiplied by. What can we say about this? If cos lies between -1 and +1, where does absolute value of cos lie? What all values can it take? Yeah, between 0 and 1. That means this is between 0 and 1. That means this number must always be less than just these two. So less than or equal to. Okay? Because this number is this number multiplied by a number less than or equal to 1, a positive number less than or equal to 1, right? And this is again an important inequality, which is called You probably heard it as the Cauchy-Schwarz, but there is another person who is it's Cauchy-Bunyakovsky-Schwarz inequality. Okay? That's an important thing to remember. Okay, and if you remember from your maybe high school physics, the dot product, if you have a vector x, the y, and let's say the length of vector x is 1, what does this give me? Gives you some number. What does the number tell me? Well, if you simply project this vector, if you drop a perpendicular line from y onto the line in the direction of x, okay, wherever this drops, right, this point, this distance is your is actually this. Okay, assuming the length of x is 1. If the length of x is 1, then this is not true. Okay. So we will later on see that the inner product actually plays a role in orthogonal projections. You're taking y and you're projecting it orthogonally onto x. An operation, an important operation that we will come across later. Okay. So now that we've defined this idea of orthogonality, we will come back to this idea of a basis. What is the basis for a vector space? Yeah. What is the basis? Okay. Yes. So the basis for a vector space is simply another set which is linearly independent and it spans the vector space. Okay. And we said there are infinitely many bases possible, right? But some bases are special. One such special class of bases are called the orthonormal bases. Okay. Let's say we have a set x1, x2, xn, which is the basis for some vector space V. Okay. That means I can produce every vector in this vector space by simply doing a linear combination of this. And there is only one way in which I can produce each vector. Okay. There is a unique way in which I can produce each vector here. We say that, and that means this is a basis. We say this is not just any basis, but an orthonormal basis if these vectors 1 to n satisfy the following property. If you take any two vectors xi, xj, okay, and you compute their inner product, it will be 0 when I is not equal to j. That means every vector here is perpendicular to the other vector. And this is equal to 1 if I is equal to j. That means the length of each of these vectors is 1. Okay. So if this is satisfied by your basis, then it's an orthonormal basis. The reason this is special is because of this. Okay, let me ask you this geometrically. Okay, let's say we are working with R2. This is the origin. I have x1 and I have other vector x2, and these two together form a basis for R2, right? Now let's say I have, if these form a basis for R2, then let's say I have another vector y. Okay, that means I can express y like this: alpha 1 x1 plus alpha 2 x1, right? Because that's the definition of basis. And there is a unique way I can do this. There is only one set of values for alpha and alpha 1 and alpha 2 that will give me this. If I gave you this picture and I gave you a ruler, right? How would you find out the value of alpha 1 and alpha 2? Then what do you have to do? You have to get to y as a sum of two vectors. If it's a sum of two vectors, that means the parallelogram law of addition works, right? So that's the clue. So you have to kind of form a parallelogram such that the diagonal or the longer diagonal, right? I don't know if maybe it's called the main diagonal. The main diagonal is your y. Okay, but what sides do you choose for your parallelogram? Well, the sides have to be these two vectors, right? And if it's these two vectors, we know where these two vectors lie. Where does this vector lie? Alpha 1, x1. But it lies along this line, right? What about this? It lies along this line. Now, how do I choose a vector from this line, choose a vector from this line, such that their addition gives me this? What would you do? How do you form the parallelogram? Well, okay, you take this line. Let's say we have the ability to move this line, generate any line that is parallel to this line, right? You then generate a line, line parallel to this line that passes through this point, right? Then I do this. Wherever this line intersects the other line, that's how much of this vector I need to take, that length. Similarly, if you take this line and you draw another line parallel to this line, passing through the tip of y, so that will be at this point. This will be your alpha 1, just this distance. Okay, you take the ruler and measure the distance between this point and this point, and you measure the distance between this point and this point. That's alpha. Okay. So if you had any arbitrary basis, right, for R2, geometrically, this is the operation you do to find out alpha 1 and alpha 2. There is a corresponding algebraic operation you can do as well. Okay. But that algebraic operation looks a bit complicated, at least with the stuff that we've learned so far. It's not clear how you would obtain the corresponding algebraic operation to get alpha 1 and alpha 2. The reason the orthonormal basis is special is this process of obtaining alpha 1 alpha 2 turns out to be extremely simple. Okay. Now, let's assume that x1 and x2 do form an orthonormal basis. Okay. Okay. Let's say we have this, this. Maybe I'll not call it x1. I'll call it z1, z2. Okay. And then I have y. Geometrically, you do the same operation to find out alpha 1 and alpha 2 here. Or let's say this is y, and I want I'll call it beta. Z1 plus beta 2, Z2. To find out beta 1 and beta 2, you do the same operation. You draw a line parallel to the vector Z2 from the tip of y onto Z1, and similarly from the tip of y onto Z2. And then wherever that intersects, that's your beta 1 and beta 2. Algebraically, if your Z1 and Z2 do form an orthonormal basis, that means Z1 transpose Z2 equals 0 and Z1 transpose Z1 equals Z2 transpose Z2 equals 1. Right? That's the definition of an orthonormal basis. Now you take this and let's say we multiply by Z1 transpose on both sides. So if you do that, you get beta 1, Z1 transpose Z1 plus beta 2, Z1 transpose Z2. Okay, we know how to do this operation algebraically, right? And we know that this term is 0 because it's an orthonormal basis. And we know what this term is, and this term is equal to 1. Right? That means my beta 1 is simply Z1 transpose Y. Okay. What about beta 2? How do you find beta 2? Well, you simply extrapolate, no? If see beta 2 is this. That's why orthonormal bases are very, very nice to work with. because you can very easily find out beta the representation of any vector y in this new basis. If it's orthonormal, finding out its representation is extremely simple. Okay, instead of R2, if it was an Rn, then you have beta n is simply Zn transpose. Okay, all right. Okay, that's about orthonormal basis. And the last uh, um, topic about basis and subspaces that we'll talk about is this idea of dimension of uh, dimension of a vector space. Right. So if you have a vector space, right, how many possible bases can we have for a vector space V? Yeah, I'm sure you know. Well, R2, how many possible bases can I choose for R2? Infinity, right? There are infinitely many bases. But what is common about all of them? Well, there is something that are common about all basis sets, right? We know at least two of them. Sorry? No, sorry, that's a vector space. A vector space is a set that is closed under scalar multiplication and vector addition. But I'm asking about the basis for this vector space. Yes, we know every basis set will be linearly independent and it will span your original vector space V. It turns out there is a third property that is common to all basis vectors, is the number of vectors they have. Okay, for example, if you're talking about R2, then any basis for R2 will have the same number of basis vectors. Okay? So all bases will have the same number of vectors. In fact, if it's R2, can you tell me a basis for R2? An arbitrary basis. Take a guess. And you only have to choose two vectors which are not collinear, and then you're done. Anything. Yeah. Go ahead. I mean, I think it's very difficult to get it wrong. Okay. Can you tell me the second one? Can it be this? Is that okay? Is that a basis? Is it linearly independent? It's got the zero vector, so it cannot be linearly independent. So it's not. So that's not a basis. What would this? Is that a basis for R2? Why not? Right. This is not linearly independent either. This one. This is okay. Okay, you can verify that it's actually linearly independent. Right. This is a basis for R2. How many elements does it have? Two. Okay. Now, you can think of other bases as well. All of them will only have two elements. And the two is essentially the dimension of R2. You can think of it as the number of degrees of freedom you have in R2, or the number of real numbers that you have to tell me for me to know exactly where you are in R2. Similarly, if you have R3, how many basis vectors will there be in a basis for R3? Well, you have to span all of R3. It will turn out you need three. Every basis for R3 will have exactly three vectors. Okay, that means in general Rn have n, and that's the dimension of your. The same thing applies for subspaces of Rn. Okay. if you have a subspace S that's from Rn, and the basis for the subspace S has m vectors, then what is the dimension of the subspace S? It's m, and m will always be less than or equal to n. Okay, means now if this is R2, the dimension of R2 is 2. Is this line a subspace of R2? Yeah, you have to go back and look at what is the subspace. Okay, well, it is a subspace because it's a subset of R2 and it passes, well, it is also a vector space by itself, so this is a subspace. What is the dimension of the subspace S? Well, if you say the dimension, then you have to ask, okay, how many vectors are there in the basis? What is the possible basis for S? Just this one, any vector from this. If I choose this, just a single vector from this subspace, that's not zero. This is a linearly independent set, and this single vector can generate any element from the subspace. That means the dimension of this, so the dimension of S equals 1. So often you will see, if you have a subspace S, you might see in the notes and on the board, we write something like this, dim of S. This is simply, dim simply is an operation that, let's say, gets a basis from S and counts the number of elements that are there in the basis, and this will be, in this case, it will be 1. Now, if you have R3 and you have let's say, this is X, Y, Z, the XY plane is a subspace of R3. Okay, what is the dimension of the XY plane, which is a subspace of R3? No, dimension of R3 is 3 because you need 3 vectors to span everything, and that will form a linearly independent set. What about the subspace formed by just the XY plane? It will be 2 because to generate any, well, a basis for the subspace will have 2 elements. What about just the Z line passes through the origin? It's a subspace. That will be 1. Can we have a subspace whose dimension is actually 0? Do we know of a subspace? So that essentially means it's a subspace which does not have a basis, or its basis set is empty because the number of elements in the basis is 0. Okay, that's the trivial subspace. What is a trivial subspace? Remember, what is the trivial subspace of any vector space? Just a 0 element. If you only have 0 element, this is a trivial subspace. You can say, okay, well, I just choose a 0 and that's the basis. Well, if you choose a 0 vector, any set that contains a 0 vector is not linearly independent. That means it cannot be a basis. That means the basis set for this is really an empty set. The dimension is 0. Yeah. Okay. Again, something that you should really remember, and this is really important. Okay. That's essentially everything that we will talk about in terms of vector spaces and some basic definitions. We will conclude the first module with the last topic on linear function. Okay. Well, what is the function? Do you remember? What is the definition of a mathematical function? If you have two sets, A and B, function is simply a table or a map, whatever you think fit, that takes elements from A and finds a corresponding element in B. And for any element in A, it only points to one element here. Okay. Well, two elements from A can point to the same element, but you cannot have one element point to two of them. Okay. Any such mapping, okay, is a function. Okay. It's essentially a table with one column being the input, one column coming from set A, another column coming from set B, and there is a correspondence between elements in the same row. That's any general function. Linear functions, on the other hand, we say a function f, and we are specifically talking. So you can have functions between any arbitrary sets, right? Here we are only going to be talking about functions from Rn to R. Simply means this is the input set, this is the output set. This function takes elements from Rn, and then this arrow indicates that it maps, okay, maps to elements from R. Okay, that means this is for the functions that we will talk about. A is R, Rn, B is R. Okay, this is again any arbitrary function. This is not a linear function. This is simply a function from Rn to R, or set of functions from Rn to R. We say that this function is linear if it satisfies the following property. Let's say we have an element x1 from Rn. Let's say this maps to some real number y1, y2. Let's say this we know. If you take x1 and put it through this function, you get some real number y1. You get x2, put it through this function, you get, and we will usually write the y1 as f of x1. And writing it like this simply means you take the element x2 and then you're applying the function f on the element x2. You take the element x1 and you apply the function f on x1 to get the corresponding output from R. Okay. Now, if you know this mapping of x1, if you know that this x1 gives me y1, I take x1 and I multiply it by some scalar, a real number, and if I ask what is the corresponding mapping of this under f, if this gives me simply this for all possible x1 and all possible alpha, okay, that's the first condition. The second one, if I take, so I know x1 maps to y1, x2 maps to y2. If I ask what does x1 plus x2 map to, and if that maps to y1 plus y2, and if both these conditions are satisfied, then I say both these conditions are satisfied for any x1, any alpha, any x1 and x2, then you say function is linear. Okay. Or another way to write this is, if I know the mapping from x1 is y1, x2 is y2, and I take a linear combination of x1 and x2, okay, and I apply my function f, and if the corresponding output is simply alpha 1 times y1 plus alpha 2 times y2 for all x1 and x2 and for all alpha 1 and alpha 2, then you say that this function f is linear. Okay. What's the definition? Okay. See, this also simply means, so you see, we can also write it like this, right? Because y1 is f of x1, y2 is f of x2. If I take a linear combination of a set of vectors, right, and I apply the function f, if the function is linear, what it allows me to do is it allows me to move this function f into the parenthesis. Okay. And that's what's happened here. So we've moved f inside. See, in fact, we can write this down a little bit more carefully here. If the function is linear, it turns out I can kind of pull the plus sign out. Okay? I can write it as f of alpha 1 x1 plus f of alpha 2 x2. Okay? Whenever you have an addition operation inside, I can move the function inside the parenthesis. Okay? This is from the second property. And the first property tells me if you're simply scaling your whatever is inside the function by a real number, that means you can pull the real number out. Okay, and this is nothing but y1 according to that. This is y2, and that's this. So this is implied by these two properties. You can't, you cannot do any of these steps if the function is not linear. Another quick way to verify if a function is linear is from Rn to R is if you input the zero vector, it should always give you zero. If it gives you a non-zero value, then it's not linear. We will quickly look at a couple of examples, right? Let's say we are talking about functions from R2 to R. This function f takes x, which is x1, x2, and simply adds the two elements together, and then returns that as the output of the function. What do you think? Is this linear? First thing you do is verify this. If you put the zero vector, do you get zero? Sorry, why do you get 1? Here. What is x? x1 and x2 are real numbers. If I put the zero vector, 0 plus 0, I get 0. So this is okay. It can be a real a linear function. Okay, and then you'll have to verify this. Okay, you can do that yourself. I won't do it, but you will find that this is linear. What about this? This a, b. I simply make one small modification. x1 plus x2 plus 2. This is not satisfied. So this is definitely not linear. But I want you to verify this using these two properties. You find that these two, one or both of them are not satisfied. Okay? This is not linear. You can verify these by yourself and then find out whether or not that's right. And in fact, the last one. W1, W2 are some real numbers. Okay. The only last thing I want to say is this. Okay. Let's say we have a linear function for R into R. It turns out that it's okay. If you consider all possible linear functions that take elements from Rn and produce R, okay, that turns out that any linear function from Rn to R can always be written like this, okay, where W is simply, okay. First time you see this, it might seem very strange, but this is in fact true. Okay. Okay. Let's say you've written a computer program. Okay. You've written some function in Python. You said def f of x, and this is a numpy.array, and this returns float. Don't worry if you don't know what that means. Simply think of it as you've written a mathematical program which takes in a vector from Rn and then does some computation. I don't know what computation it does, and then simply returns the result. Okay, this result is a float, a real number. Okay, and let's assume I don't have access to this. And if I really wanted to know what is inside the code in Python, you can find out. But let's say I don't want to put in that effort. You've given me this function, and you've told me that this is a linear function. Okay, if you give it a vector in Rn, it'll produce an output, and that mapping is linear. That means it satisfies these properties. I can verify it for a bunch of numbers and see, okay, it does look like it's linear. Okay, let's say I don't want to use your function. Okay, because it's too painful to download your library from GitHub and then integrate it into my program. Every time I want, let's say I want to install a new version, I have to do this. Let's say I don't want to do that. I say, okay, I know that if your function is actually linear, then there is a representation of your function that is of this form. Okay, that means to know your function entirely, completely, right? All I need to know is find out this W vector. Once I know the W vector, let's say I know the W vector and I have a new vector y for which I want to compute the output of your function. I can do two things. I can call your function with y, and this will give me my result that I want. But if I've already figured out w for your function, then I don't have to call your function anymore. I simply take y and I basically take the inner product of w with y, and I'll get the result, and both of them will match. Okay, that's what this means. That means you can always find a representation for a linear function from Rn to R using just a vector from Rn. Okay. You'll see in the assignments why this is true. This is true primarily because linear functions have this structure. And I think one of the assignment problems is if you have a function like this, or maybe it's in the notes. If you have a function like this, how do you actually find out this w? So that you don't have to call the function, you only have to do an inner product between w and x. Okay, so I encourage you to go through the notes to see how you do something like this. And the reason you're able to do this is because of the structure of linear functions. Okay, so that's all we have for the first module. If there are any questions so far, we will talk about them. Otherwise, we'll move to the next one on matrices. Maybe yeah, matrices.